What is signal processing? It's good to know the answer to this question at the outset, seeing as this course is all about signal processing. As you know, signals convey information. We manipulate signals, or process them, to change their information content, or to change how the information is represented in the signals. Why process signals? Signal processing is done for a reason, and that is to achieve some useful purpose. There are so many applications of signal processing that all cannot be listed, but here's a short list of some that come to mind. 1. Communicating between two different locations using cables, optical fibers, or the wireless electromagnetic spectrum requires lots of signal processing. 2. One may determine an object's location using GPS or radar, for example. 3. Reducing the size of a data file without losing any information allows us to use data memory more efficiently, and also shortens the transmission time of that signal. 4. Whenever a signal is eventually seen and/or heard by a human, it may be possible for signal processing to improve its perceived quality. 5. There is always something interfering with our signal transmissions, such as naturally occurring background noise, which in many cases can be overcome using some pre- and post-processing of the signals. 6. The information content of a signal may be encrypted to keep it secure from unauthorized observers, or the signal itself may be hidden so that others may not even suspect that it is there. 7. Image processing to detect faces is an example of feature extraction. And 8. The response of a system, such as a fly-by-wire airplane, may be controlled using feedback signals from various sensors. This too is an important application of signal processing. One of my favorite examples, showing the importance of signal processing in our daily lives, is how speech is sent from one mobile phone to another. This task is far more complicated than you may think. First, the sound pressure waves in air near the speaker's mouth are converted to an electrical waveform using a microphone and amplification circuitry. Then, some type of low-pass filtering is done to this analog signal in order to prepare it for sampling. The carrier of speech information is changed from being an analog waveform to being a list of numbers using analog to digital conversion. The list of binary numbers is compressed in size using a digital computer algorithm, one that has been specially tuned to remove redundant information from speech samples. Packets of bits are formed from the compressed speech data and also other information that specifies time, source, destination, and who is being charged for the call. Error-correcting bits are also added to better improve the integrity of each bit packet as it is sent from source to destination. The digital bit packets then modulate a high-frequency analog waveform to prepare for transmission. After amplification, the signal is fed to an antenna, where energy is transferred to the electromagnetic spectrum. This EM wave travels wirelessly through space, from mobile phone to the nearest cell tower. The cell tower's antennas receive and demodulate the signal to reconstruct the packets of binary data. At this stage, the bit packet enters a cell phone company's communication network and is routed over wire or fiber optic cable to its destination. If the final destination is another mobile phone, another cell tower retransmits the information wirelessly to the receiving phone, whose antenna and electronic circuitry amplify the received signal to produce an electrical waveform. This electrical signal is demodulated to recreate the packets of bits, which are separated into their components to recover the compressed speech binary codes. A computer algorithm synthesizes samples of the received speech signal from the binary codes, and sampled values of a speech waveform are thus reconstructed at the destination. Digital to analog conversion changes a list of sampled values back to an analog waveform, which is amplified using analog circuitry, and converted to pressure variations using a loudspeaker near the listener's ear to complete the speech process. Thus, the speaker's voice has been processed many times, in many ways, to finally be heard at the receiver. Curiously, the speech being listened to is nothing like that which was spoken in terms of wave shape. The speech coding process essentially pieced together parts of other people's speech to create a signal that sounds like the original.